That,
Okay.
So
Hello, everybody. Yeah. Okay. Hi. So, welcome to this short workshop today. We have Karthik Tiwari with us. And just a couple of weeks ago, in the lockdown season, he wrote a paper about certain trends and patterns in how the COVID-19 cases are spreading around the world. And he'll definitely be able to tell you more about it. But also, we wanted to bring some focus into the Matplotlib library of Python today because it's such an important and effective tool for plotting anything you want, right? And I think if you're someone who's working with any form of data, irrespective of which field you're in, Matplotlib is a great skill. So we will start with a small intro to Matplotlib for those of you who maybe want to refresher, or you want to learn it, and you can go ahead and learn more about it later, at least get a glimpse of it today. And then we will speak about COVID-19 data in specific. I think we have a bunch of participants here who have a lot of doubts today. So please be interactive. You can interrupt him at any point and ask him what you want to ask him. So yeah, let's get started. Cool. Welcome to the workshop, Karthik Tiwari.
thank you so much. So the way I am planning on doing this is I will obviously first talk in general about Matplotlib and just plotting and graphing things in general. Then I'll go and talk about using real world data, unpacking real world data, and then we'll move on to the dynamics of an epidemic spread. So I think I'll start sharing my screen now. All right. So the very first thing is that even if you know like elementary Python, you should be able to follow along. But if at any point of time there is something or there's something that's confusing, or I use certain parameters that you're not able to understand, feel free to interrupt me. Um, all right. So we'll be using Matplotlib, obviously, and we'll be using this other library called NumPy, which is again a very common library. We won't be using a lot of NumPy features. I am just more comfortable with having arrays which from NumPy. So there's that. So here we're importing Matplotlib pyplot as PLT, and the people who know Python, they know that using this particular syntax means that I'm calling matplotlib pyplot and I'm naming it plt. So the next time I want to use something from that library or package, I don't have to write the entire thing. I just write plt. The same with numpy. So I'm calling numpy and I'm calling it np. So the way matplotlib plots things is it takes in so in this particular example, it's taking in two arrays and it matches the index values. So the first number here and the first number here, that's a point on the graph. The second number here, the second number here, that's a point on the graph. The third number here, the third number here, that's a point on the graph. So this is basically what's happening. So we have one list, we call it x1, and it is a list that goes from 0 to 6. And then there's another list, we call it y1, and that's basically the square of all the numbers in the first list. And the syntax is just this: plt.plot x1 comma y1, and this plots the first list against the second list. But in most cases you don't really write both the lists. What you do is you have a certain input values and then you have a certain function that returns another value. So we make another list that's again going from 0 to 6, and this time what we're doing is the second list, we're not writing it manually. We're just telling Python that, okay, we have this one list. I want you, Python, to cube all the values in that list and then make another list, and we call it y2. So it takes all the values from the first list, it cubes those values, and then we use the same the exact same syntax, that is plt.plot, and then this plots um, all these numbers and their respective cubes. Now there's this thing, like it's so okay, I am a physics student and I usually don't when I'm making graphs, I always try to um, I always try to incline towards utility and not as much as the aesthetics of the graph. So there's this thing that when you're making graphs, when in a case where you have experimental data and you're making a graph, then
Hello.
what you try to do is you don't plot a continuous line, because that means that you are so the reader would feel that you have data for the points between the points that you have plotted as well. So in this case, in this case, we have 7 values and then we have seven outputs, but we don't know what's the cube of 0.5, right? In this particular data set. So what we do, for example, you've performed an experiment where you took 3 different values of a certain parameter and then it gave some other result, and you don't know what happened in the middle of those. So you do these things called scatter plots, and then you make a trend line between those scatter plots, to say that okay, these are the values that we know, and this is the expected trend. And the way you make a scatter plot in Matplotlib is by using plt.scatter. So these are the exact same list that we used before. This is x1, y1. X1 is a list that goes from 0 to 6, and y1 are the squares of those values. And x2 is another list that goes from 0 to 6, and y2 are the cubes of those values. And as you can see that this is these are the values of squares and cubes of 1, 2, 3, 4, 5, 6. Now here we made one list manually and then we computed the other one. What we generally do is we don't even make one list manually, like we don't type out things, because usually we work with bigger data sets. So we use this other function called np.arange, and what it does is, so the parameters that you given are the starting value, that is 2 pi minus 2 pi, and the last value, that is 2 pi. So what we're asking Python to do is that create a list for me that goes from minus 2 pi to 2 pi with the intervals of 0.01. So if I um, print this list, you'll see that it goes from minus 2 pi to all the way to 2 pi with the intervals of minus 0.1, minus 0.01. Now what we're doing is we have one list of all the values ranging from minus 2 pi to 2 pi, and then we make another list where we ask numpy to calculate the sign of all of the range of these values. We make another list that's for cos, and then we plot this, and we have this sine curve. All right. Again, the point is that you don't even try to write the input parameters usually manually, because so what happens is that right now this is a really smooth curve, right? If I change these intervals, and this would if I change the intervals of the input values and I print the list again, then you'll see that these are intervals of 1, right? What will happen now in the plot is that the plot would not look so fine. So like the smaller the intervals are, the smoother your curves will become. But again, that comes with the added factor that the more values you're computing, the harsher it's going to be on memory. Now if so as you remember, we also calculated the cost values of all these input values. So we can also plot two graphs, two curves on the same graph. So the orange one is the cos curve and the blue one is the sine curve. All right. And this is what happens if you just type plt.plot multiple times. It what Matplotlib does is it plots the same values, it plots the same curves on the same graph. it plots the multiple values on the same graph. If you want to plot them on different graphs, then what you do is you use this function called plt.show, and it basically shows all the values. It basically plots all the values before plt.show, and then after that it clears the canvas and starts making another graph. So if I do this, then I have one figure where I have the sine curve, and I have another figure where I have the cos curve. So this is what happens. This is what you do if you want to plot multiple curves and multiple graphs. Now all these graphs were like specifically for introductory purposes. These are not very useful graphs. One example of a useful graph that you might actually come across, or a useful function that you might come across, is one that we'll be discussing now. So here what I'm doing is I'm defining a function called kinematics, and this function takes in two input parameters. Those are time and acceleration. Okay, and these two are just, if you remember from high school physics, these are just equations of motions. So we okay, yeah, these are equations of motions that assume that the initial velocity of a certain body was zero. So v is a into t, because u is zero. So v is a into t, and acceleration into time, and s is the distance covered. So that's half at squared. Okay, so it takes in two values, and it computes velocity and speed of that body on that particular time, on with that particular acceleration. So it takes in two values and then it returns velocity and speed. Okay, now we'll be using this function, this kinematics function, to plot the motion of a body. So I again create input parameter, an input array t, an input list t, where which basically goes from 0 to 10. These might be seconds, these might be, yeah, these are definitely seconds, with the intervals of 0.1. So if I type out t, this is what it will show. This is just a list that goes from 0 to 9.9 with the intervals of 0.1, 0.2, 0.3, 0.3, 0.4, all the way up to 9.9. So this is, we created an array for input values, and we created a function called kinematics that basically solves equations of motions. Now what we're doing is, we're creating other lists that we want to plot against time. So this is v1, which is velocity of the first body, and I'm assigning a list. What I'm doing is I'm computing the function kinematics for the range t that I just made, which is displayed here, and the acceleration I've given is 9.8 meters per second. So that's the acceleration due to gravity on Earth. And so the square bracket 0 here, what happens in Python is that Python starts counting from 0. It doesn't count from 1. So what kinematics function is giving me are two values. What I want is the first value, but to Python, this is the 0th value. So usually we count 1, 2, 3. Python counts 0, 1, 2, 3. So if I want Python to give me only the first value, then I'll have to ask Python to give me the 0th value. So I make a list, I make an array, which is v1, and what it gives me is kinematics, the first output of kinematics. I make another list of speed. I make another list of velocity, which again takes in the same time input that is displayed here, but this time for a different acceleration, 1.6 meters per second square. That's the acceleration due to gravity on moon. And again, it's taking the first output, the 0th output of the kinematics function. So I did that for velocity. We repeated the same thing for distance traveled, and distance traveled for the first body with an acceleration due to gravity of 9.8 meters per second. And the one here represents that I'm asking Python to only include the the distance output, which is the second output in layman's terms, but in Python's language, it's the first output because it's counting from zero. So I now have one list that's basically time. Then I have two lists for velocity of two different bodies, and I have two lists for distance traveled by those two bodies. Now what I'm gonna do is I'm gonna plot time and the velocity of the first body, and I'm going to plot time and velocity of the second body. And as we just saw that if I'm not typing plt.show, then Python is going to plot both of these curves on the same graph. Now, of course, we need to be able to see and understand what each line represents, right? So we also give labels. So the first one, because it had 9.8 meters per second acceleration, so I'm labeling it Earth. So this is the velocity on Earth of a body falling under gravity, and this is the velocity with respect to time of a body falling on the moon. And as every high school teacher keeps reminding everyone that always label your axes. So we're labeling our axis here using the function x label and y label, and the x-axis is just time and the y-axis is velocity. And we also give a title to our graph using plt.title, and this is the velocity graph. The legend here, so I've labeled the curves, but if I don't ask Python explicitly to put the legend there, it won't show the legend. It knows which curve is which one, but it won't display that. So I need to also write plt.legend, and you can also manually tweak where you want this legend to be. But usually usually Matplotlib does a really good job of figuring out what is the best place to put the legend. It tries to find the corner where there are no lines and where there are the least number of lines, and it puts it there. So again, there's another thing. Some people like grids on their graphs, some people don't like grids on their graphs, and grids definitely serve a utilitarian purpose. In certain graphs, it's just incomprehensible to understand what the curves represent without having a grid. So the way you put a grid is just by plt.grid, and this will show you the grid. So this is a graph of velocity of two bodies falling on Earth and on Moon with respect to time. As you remember, we also calculated the distance traveled by them. So we'll also plot them, the distances traveled by the two bodies here. And we're doing the same thing. We're labeling each curve. So the first one is the body on Earth, and the second one is the body on Moon. We're labeling the axes. We're giving the plot. We're giving the figure a title, and then we're displaying a legend. We're displaying a grid. So this is the other graph. Now you might have noticed that there are certain parameters here as well. These are for formatting the curve. So R here represents the color red. As you see, the Earth curve is red, and the double dashes represent what kind of a line I want. So this is a dashed line. The this represents this sort of a line where there's a continuous line and then there are points. So these parameters are used to tweak what the curves are looking like. This is red, this is green. You can also specify color using hexadecimal values if that's what you're comfortable with. And Python also has a list of colors. Like if I type red, then Python will also recognize that. Now, sometimes what you want to do is you have this big graph, but you only want to look at a small part of the graph. So for example, I just want to compare the motion of these bodies in the first 2 seconds. So what I do is I ask Matplotlib to put a limit on the x-axis, and now what it will do is it will only show me the distances traveled by them in the first 2 seconds. Now, as you can see, this is not a really useful graph because the y-axis goes all the way to 500, and all these and the distances covered by the bodies are just squished down to the bottom. So we can also put a y limit, and Now it only goes all the way up to 30, and that's why you can see like a proper magnified version of the graph. And again, you can see that this is the body falling on the moon, and this is the body falling on Earth. And you can use xlim and ylim to tweak how much of the graph you want to see and you want to be displayed. The last statement here, plt.savefig, again does exactly what it says it should do. It saves the figure, and the values inside the parentheses, they're the name of the graph. So if I run this command, what Python will do is it will save this figure within the folder where I have been running my code. So I have this folder called COVID-19 plotting, and I've been running this Jupyter notebook, and it has saved this graph here. So we have this graph saved, and this is a useful thing because most of the times whenever you're making figures, you want to use those figures somewhere in probably your LaTeX document or something. So this 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 is how you this is pretty much the basics of plotting. And the thing with Matplotlib is that it's a really powerful software. It's a really powerful library, and it's enormous. So, but the good part about it is that it has a really thorough documentation as well, and it's also very intuitive at times. So, for example, save figure is exactly what it sounds like. It saves the figure. Xlim, ylm, they're exactly what they sound like. So most of the times, like the best way to learn Matplotlib is by just trying to plot things and just going through their documentation and figuring out what you want to do and tweaking certain parameters of the plots. Now this is the last part of the introduction to Matplotlib Jupyter Notebook. And what I'm discussing here is, so sometimes what you want is one figure but multiple graphs on it. So this was one graph and one figure with multiple curves. Sometimes you want multiple graphs and multiple curves. So what you do for that is you define one figure. So I have one figure. This can be so there's this one figure, and and then what I'm saying is that, listen, I want one figure and two graphs, and these two graphs are what Matplotlib calls subplots. And the values inside the parentheses represent that I want two subplots, and I want one row and two columns. So what this will display is two graphs in one row and two columns. And again, what this is saying here is just setting the figure size in inches, and this subtitle is like the super title of the graph. So what I can do in these graphs, so first of all, this is one row and two columns, right? I can give, and Python is considering both of these as separate graphs. I can tweak the parameters of these graphs independently, or I can tweak the parameters of them um, at um, I can tweak those parameters together. So one thing is that I want both of these graphs to have the same title, that is falling bodies on Earth. So in one of the graphs, I've plotted velocity as a function of time. So velocity is a linear function. It's just acceleration into time. So it's a straight line here. And I've plotted the distance traveled by those bodies with respect to time. So this is a quadratic function because distance traveled is half acceleration into time squared. And I've given the x label and y labels independently. So in the first graph that I've called ax1, in the first graph ax1, I've set the x label as time. Okay, so this is one of the minor annoying things about Matplotlib, that when you're working with just one graph, it has different syntax, and when you're working with like subplots, it has different syntax. So if I want to name the x label of a subplot, then I use set underscore x label. And if I just wanted to set the label, I usually would have just used x label. So I've set the x label and y label as time and velocity and time and position. So this is time, this is velocity, this is time, this is position, and this is how you plot multiple graphs on the same figure. And this this should like this, whatever you've learned in this particular Jupyter notebook, that should be enough for most of your plotting purposes. Like um it Matplotlib is, it's enormous, but a lot of the times what you'll be using are like very, very specific niche components of Matplotlib. So this Jupyter notebook would be available to you. You can play around, you can try to tweak colors, you can try to tweak the size. One last thing that I didn't mention in this particular introduction to Matplotlib Jupyter notebook is these universal parameters. So what I can do here are like set universal parameters for all the graphs that I'll be making. And this one is just deciding the figure sizes, and this one is the font size of both labels and the title. So if I run this now, if I make a graph, for example, this would be a much bigger graph with much bigger font size. So you can also define these parameters universally, and this should be it for the introduction. So like after this, whatever I'd be speaking about, you should be able to follow at least the Matplotlib part. And if there are any questions about Matplotlib, if you want to stop me here, please do before I move on to the next part.
Hello. So
Yeah.
hello, sir. Could you explain the first part alone?
The first part.
The first few cells. Yeah.
The first cell.
Yeah. That.
Okay. So sometimes what you'd want to do is you want certain parameters to remain constant in all the graphs. All right. So here I can what I can do is Matplotlib has certain default values for certain parameters. So Matplotlib by default makes a certain size of the graph. It uses a certain font size. It uses a certain font. If you're suppose you're making a document where you want to have all the font families to be Times New Roman. So what you can do is, instead of defining that, okay, I want this sized graph and I want this particular font every time you're making a graph, you can set these universal parameters. And the way you do that is by using plt.rc params. And here are the two universal parameters that I have decided here are the figure size, which is 12 by 8, and the font size, that is 16. So I can tweak this as well. I can make it 20. Now every graph that I'll be plotting here will have these parameters. So all these sizes were the default Matplotlib sizes. Now I've defined the new universal parameters. Now if I run these graphs, they're all going to be bigger with bigger font sizes. And this is pretty much it about RC params.
So RC params is a predefined one.
RC params, they have default values. If you don't define them manually, they'll have default values. But if you want to tweak them, what they will do is they will change these parameters for all the graphs until you explicitly mention in one of the graphs that, okay, this is not the size I want. So for example, all these graphs are following the sizes that I mentioned in RC params. But for this one particular graph, I already decided that, okay, this is the size that I want. So it follows that size, and it only changes the font size because I've manually defined that for this one plot, I want different sizes. Otherwise, for all the plots, follow these universal parameters that I've initialized in the beginning.
Okay. So we should use that figure.fig size and font size, right? So those are also predefined ones. Okay. And that plotting thing, right? The plt.plot x2 y2. So it plots all the arrays.
Yeah, it plots. It only plots whatever values it knows of. So this is a list of these 7 numbers. I'm creating another list where I'm taking the cube of all these 7 numbers. So Python only. So when I'm plotting this, the second list is also only 7 numbers. So it knows the cube of 4, it knows the cube of 5, it knows the cube of 6, but it doesn't know the cube of 5.5. It doesn't know the cube of 4.5.
So it
So
automatically creates a list y2 with all those y values, right?
yeah, it automatically creates a list of the same size, um, where it has changed these certain parameters. So for example, if I don't want the cube, maybe I want a linear function where I'm multiplying all these values by, say,
1.
pi.
Okay.
So what it will do now, it will create another list. I mean, it will update the values in y2. It's not going to create another list. And now what it's going to plot is a linear function where all these numbers have been multiplied by pi. So this is a
Okay.
linear function, and at 1 you know that the value of pi is 3.14, and at 2 it's going to be something else, at 3 it's going to be something else. So
Okay.
it only matches indexes. So the best way to understand what Matplotlib is doing is it's matching indexes. It's taking the
Okay.
first value from both the
Okay.
lists and it's putting a point there. Then it's taking the second value from both the list and it's putting a point there. And now it's using those points to create a line. And then
Okay.
and it does that continuously for all the 2 points, all the points in the graph. So it takes these 2 points and then it makes a line here, then it takes these 2 points and then it makes a line here, then it takes these 2 points and then it makes a line here. So that this is what Matplotlib is doing. So it's making a straight line between those 2 points. That's why you'll see that this is not a smooth curve. But if
Okay.
I so this is not a smooth curve, and the same happened here. So uh, if I
Karthik, can
this
you
is
zoom in a bit? The font
yeah
size. Yeah.
yeah. So this is not a smooth curve because what Matplotlib is doing is it's taking -2 pi, and the next value that it's taking is minus pi, and it's making a straight line from there. What you're doing is
Right.
you're discretizing the problem. So it doesn't, so infinite number of numbers exist between any two numbers, right? And you
Yes.
can't expect Matplotlib to know all the numbers. So what you
Yeah.
do is you choose the level of precision that you want for your problem, and then you work with that.
Okay.
You can always go all the way to, like, I can always write minus 0.0001, and now it's going to make a list and it's going to be a really smooth curve, but now it's going to take so much time on my computer
Okay.
to run. So you have to
Right.
strike a balance between the precision you want and how much of the
Uh,
curve. The thing to remember, I think I'll have to wait out for this to compute. Until then, if there's any other question, yeah. So it was asking my computer to give it like 9.36 gigabytes for an array, which would have been an enormous, like, even with
okay.
like Ryzen 5 and 4500U and like an SSD, my computer wouldn't have been able to do that quickly enough. So this is a smooth enough curve for our purposes. But the point to remember is that if you can zoom in enough on that curve, it's not a curve. It is basically a compilation of straight lines that are too fine for us to make out. So that was it. Like, are there any other doubts about
Ah,
Matplotlib?
no. Thanks a lot.
All right. Is there anyone else who wants to ask something about Matplotlib? Okay. In that case, we'll move on to using real world data to
Okay.
visualize um, uh, the spread of COVID. And again, so like this time, so this in this Jupyter notebook, we're using real world data.
Okay.
And then we're going to move on to another Jupyter notebook. And I think before that, we'll do like something fun. And then we'll move on to the other Jupyter notebook where we'll be understanding the dynamics and how an epidemic spreads. So again,
Okay.
I'm I'm uh, I am going to import NumPy as we did in the last
Okay.
Jupyter notebook, and I'm going to
So
yeah
so there's a as keyword, right? So you're assigning it default your own name, custom name as NP.
yeah yeah yeah. if I don't do that, then every time I'm calling numpy, I'll have to write the entire numpy. Like I'll have to type out numpy. So for example, I want if I want to use pi, if I want to
Okay.
use the value pi, then
Okay.
I'll have to type numpy.py. But now I can just
Okay.
type np.py. So I'm importing
Okay.
numpy, I'm importing matplotlib, and I'm importing this other library called pandas as PD. And what
Okay.
pandas is going to do is it's going to help us. It's basically going to help us work with data. It's going to make it easier for. It's going to make us. It's going to make it easier to unpack data. It's going to make it easier to manipulate data, to do
Okay.
all kinds of stuff with data. And
Okay.
again, just like Matplotlib and NumPy, Pandas is also a enormous library, and it's really thorough, and it too has a really well written documentation. So if you want to play around with these things, feel free to do that. That's literally the best way to learn all these things. So
Thanks.
we're universally defining a figure size that's 20 and 10, and we're importing numpy, we're importing matplotlib, we're importing pandas. Now what we're doing is we're going to read the COVID data file. Okay. Now where did I get this COVID data file? You can just type COVID data CSV, and you'll be able to download the COVID data files. So you'll be able to download these files. Now there are different formats in which these databases are available. The one which I prefer to use is CSVs. CSV stands for comma separated values. And even though it says comma separated values, you can separate these values by pretty much anything you want. Like you can use tab, you can use triple spaces, you can use anything to separate these values. Now, if I open this COVID data in an editor, so I downloaded that data from the website. Now, if I open it in an editor, what it's going to look like is just a bunch of numbers separated by commas. Okay, so in this particular file format, what's happening is that every new row is separated by enter, and every new column is separated by a comma. Okay, now this is what it looks like, but the way Python is going to read it is in this more decent format. So all these values are separated by commas, and this is a huge database. So it's a database of all the country of a lot of countries from a lot of different continents. This is Afghanistan, Albania. There's going to be India somewhere there, and a lot of different values for those countries. So it has dates, total cases, new cases, total deaths, new deaths, cases per million, and it has a lot of different values. So certain data is not available for certain countries, but there are all kinds of data available here. There's population density. There's going to be diabetes prevalence, number of smokers, hand washing facilities, hospital beds. This is an enormous database, and that's usually how most of the databases are. They're usually way too big. And so what we're going to do here is we're going to use pandas to read this file. Okay, so I asked panda to read this comma separated file, read the CSV file, and inside this function I'm just typing out the name of the file. Okay, so this is read CSV and COVID data.csv, and since the file was already within the folder that I'm working in, I don't have to explicitly mention the path of the file. Now what it's doing is it's reading all the data and storing it in the variable data. So this variable data, it has all the data that there was in the CSV file, but we don't need all that data. What we need is just a handful of stuff for this example. So what I'm doing now, so for example, we need the total number of cases, the date, the deaths, and the new cases per day. And the way we separate these values, the way we use these values, the technical term is called splicing. We're taking the important bits of the entire array and we're taking a simple slice of it. There's one hard way to do it, and then there's an easy way to do it. There's a quick way to do it, which is easier to understand. Then there's an so there are different ways to do it, and I'm going to explain two of them. One way to read these data ranges is by splicing manually. So what I've done here is, so if we go to the COVID data file and I search India here, you'll see that the data for India starts from the 10,606th row and goes all the way to 10,779th row. So these are all the rows that have the data for India. What I'm doing here is I'm just taking so from the database I imported these four useful values. So I imported date, total, death, and new. So these are the columns that I imported. I did not import hospital beds, the number of female smokers, the number of male smokers, because that just wasn't important. And the way what I'm doing here is I'm creating a list called date, and I'm assigning date column from the data. And if you remember, data was the variable that we assigned all the values from the CSV file. So first of all, what we did was we read the CSV file. We created a variable called data. From that variable, we took the column called date, and then we assigned it to another variable called date. From that data, we took the column total cases, and then we assigned it to a variable called total. So this is the shorthand way of doing this. Like if I write x is equal to y, x is equal to 10, y is equal to 20, and z is equal to 30. This is the same as writing x, y, z is equal to 10, 20, 30. So this is the same. Like Python reads both of these styles as the same. So what I'm doing here is I'm creating these four lists and I'm assigning these columns to those lists. Now, again, as I said, so if I see one of these lists, for example, if I see death, it's an enormous list. It's 25,000, almost 25,500 entries long. But we don't want, the reason why this is so long is it has repeating values for all the different countries, and I don't want all the different countries. I only want the values for India. So what I'm doing is I'm splicing the list, and as we just checked, the values for India, we just observed that from where does the Indian data start and to what range does the Indian data go, and that's what we did here. So we took the entire column of total, and then we only took these certain values from 10,606 to 10,779. We did the same for all these different columns. So they're going to have the same row values, right? So I made a new list called total for India. So total India, dates for India, deaths for India, and new cases per day for India. And then I spliced these values from the entire columns. I hope I'm not going too fast. Are there any doubts? I'll just stop for a second, because this might have been slightly confusing if you haven't worked with CSV files before. Also, I'm not seeing the messages, so if anyone's seeing them, okay, I'm expecting that there are no doubts until here, so I'll move forward then. So what we did is we took the entire data set, then we took certain columns from those data sets, and then we took certain rows from those data sets. And now what we have are total deaths in India, dates in India, deaths in India, and new cases in India. So this was the easy to understand method of taking the useful information. There's an easy method that's not so easy to understand, and that that is what I'll be explaining now. So there's this function called lock. What it does is, okay, so what I'm doing here is I'm setting an index value, that is location. Okay, so the index, so basically it now all the data in this data set is against this location column. So if I type, so basically what it did was it set the index as location, which is so it basically tells Python that, okay, the entire values in this data set are against location, like they are with respect to location. Dot head, okay, I don't think I need to go into dot head, but now what I did is I asked Python to locate all the locations where the value of location column is China. So what this did was it created a new array. It took from that entire data set, it took all those values where location was equal to China. And now I have a separate data set where it's only which only includes all these details for China. And again, now this even though this entire data set is for only China, it still has all these things that we don't need. Like, for example, we don't want extreme poverty, the fraction of people living in extreme poverty and stuff. So what I'm gonna do now is from within this smaller data set of China, I'm gonna make okay, I'm gonna make newer columns where I'm gonna use all the important all the columns that we need to use. So just how we made total cases in India, date for India, deaths in India, new cases per day in India, we're doing the same for China. So but now we don't have to go and manually check the row values, the index values. Now, since it only has data for China, I'm going to ask Python to, in the new data set called China, I'm going to ask Python to take the entire column of total cases and make a new list called total China, and store all those total cases, store the entire column within this new list. And I did that for dates, deaths, and new cases per day. Okay, so these are the two different ways of splicing data. One is manually doing this, and one is using the functions built into Panda. And now we have these values for India and China. Now we're going to do some plotting. So what we're
Hello.
going to do now? Yeah.
Hello,
Yeah.
sir. What is that? Dot set index location and in place is equal to true.
Okay, so most of the times, almost all of the times in pandas, whenever you want to do any sort of manipulation in a data set, you just have to type this out, in place is equal to true. Otherwise it doesn't apply the changes in the data set. So you'll see this in several places, wherever I'll be using pandas to do, okay, yeah, here, wherever I'll be using pandas to do some certain manipulation in the data set, it just this is just a thing that you have to do. Like, there's always there's obviously a purpose for it, but for now you just have to remember that if you don't write this, or if you write it as false, then it won't change the data set in any manner.
Okay. So
Right.
does it completely change the data set? Writing in place is equal to true.
Yeah,
It completely modifies.
yeah. So now this index has been set to location. Now if
Okay.
I want to set the index to location again, it won't be able to do that, because index is not a part of that data set. Index is the thing against which the entire data set has been plotted. So this has permanently changed the data set now. So if I want to so what you the error came before as well, right? So what I did was I imported the data again, and then now I have a fresh new unchanged data, and now I set the index, and now I could do that. Okay, so we have these values for,
And
yeah. Yeah. Okay. I'll move on then. So as I talked in the previous Jupyter notebook, we're making one figure, but the difference is that we're not making separate. We're not making multiple graphs. So we're within the one figure, we're making one graph, and so even though it says subplots, what I'm asking Python to do is I want one row and one column, which just makes space for one graph. And now what I'm going to do is I'm going to make a scatter plot where I'm plotting the total cases in India against time and the total cases in China against time. And what this is going to do is, as we remember from the last notebook, that it's going to plot both these things as a scatter plot. That these are not going to be continuous lines; they're going to be dots on the figure, and both of them are going to be same. Both of them are going to be on the same figure. They're not going to be on different figures. Also, like I briefly mentioned it in the last Jupyter notebook, but Matplotlib has its own ranking of colors. So the first color is always blue, the second color is always orange, the third color is always green. You can manually change it, but even if you don't, it will always assign different colors to different graphs. So I'm doing this. I'm plotting these two things. Now, okay, we'll go through these one. We'll go through this one particular function after I've run the cell. So it's gonna take some time because there was so much data. Okay, so if you look at this graph, the very first thing you're gonna notice is that there is this huge black smudge here. And if you think about it, what it is doing is it's plotting data for every date from this first reported case all the way to yesterday. And the problem is that that is just too many dates to display here. And that's why these grids also look so fine, because there are just all these dates have been squished, and they've been so squished together that you can't even see what's happening. So I'm gonna ask Python to to put a limit that the most number of ticks I want. So these things here and these things here, they're called ticks in Matplotlib. So the most number of ticks I want there are 15. I don't want it to display more than 15 dates. And that's what that statement did. So now it automatically took the entire range, it divided it by 15, and it placed 15 equally distant date values here. So now it looks more legible. Now you can actually see that on 1st March there were these many cases in China and these many cases in India. So okay, oops, these are total cases in both. So as I said, the first color is always blue. So this is the total number of cases in India. And as we can see that China had an outbreak earlier, India didn't really have an outbreak until much later, but China has it under control, and India it's still growing exponentially. So you can do this, and what the way I did that is by so I'll just briefly go over everything I did again. I took the entire data set, and then I took the separate values for certain countries, and then I took the columns that are going to be useful. And then I plotted two of those columns against each other. So dates in India against total number of cases in India, dates in China against total number of cases in China. The good thing about this particular data set is the fact that the dates are the same. Like, so even though India did not have any cases when China started experiencing cases, it still reports Indian cases as 0. So you don't have to worry about the different axis sizes. I'll go over this cell slightly later when we'll be talking about the dynamics. But this is one of the graphs. This is one of the simplest COVID graphs that you'll see, which is just all the total cases in India and in China. Now, in this graph, what we're doing is first of all, we're making two graphs in the same figure. And unlike the previous example where we had two columns and one row, now we have two rows and one column. So the first value is rows and the second value is columns. So it's going to make a figure that has two rows and one column. again, I set the title for the individual graphs. So the first title is um, new cases. Yeah, this is just a typo. So I set the title for the first graph. I call the first graph AX1, and in AX1 I'm plotting date in India against number of new cases per day in India. So these are not the total cases, these are the number of new cases per day. And I'm doing that, and I'm calling this new cases in India, and I'm doing that for China, and I'm calling it new cases in China. And as we did in the last graph, that we had to define that, okay, we only want 15 dates to be displayed, otherwise it becomes a huge black mess. So this is a graph where we have the number of new cases, reported cases every day, and we have number of new reported cases in China every day. So this is India, this is China. And as you can see, as you would expect, that when China was reporting its cases, there weren't a lot many cases in India. So when China was experiencing a huge problem, there weren't a lot many cases in India. But now China has, so like now there aren't a lot of new cases in China, but India, it's going, um, it's bad to say the least. One thing to notice is that the ranges for these two y-axes are the same. So it's not like uh, these graphs are stretched or magnified out of scale. This goes from 0 to 16,000. This too goes from 0 to almost 16,000. And this huge blip you see here. So this is just a thing that. So what happens is that a lot of times people report these cases late. For example, if I go to Indian, uh, for example, if I go and see Corona India, oops. You'll see that on one particular day, the number of daily deaths rolls all the way to 2,000. It's not like suddenly 2,000 people died. It basically, what it meant was that people had died, and those 2,000 reports were verified and reported on that day. The same happened here. So like, these are number of new recoveries, and then this even made headlines in newspapers that suddenly one day, um, the number of recoveries rose all the way to, okay, wow, this is bad UX design. um, it rose all the way to 11,707. This doesn't mean that 11,000 recovered miraculously on the same day. It just means that the reported dates were late. That's basically what happened here. So this huge blip. So to one way people take care of this is by smoothing out the curves. So instead of reporting every single day's data, they take in a series of days, for example, a week, and then they average it out. So it smoothens the curve. So even if you see here, you'll have an option to smoothen the curve, like 7-day moving average. So this is a smoother curve, right? Because here you had a big blip. Now this almost smoothened it out because it was taking the average. So that's one trick that you can use to take care of these anomalies. So this is new number of new reported cases every day in India and China. And I mean, this is pretty self-evident that all of us need to take all the precautions and stuff, because it's going bad. So the thing is, so one important thing to notice here is that it's not going to drop all the way to zero one day. It's going to go, and it's going to peak, and then it's going to fall down. And right now our curve is only on its rising edge. It's not going to become zero, or it's not going to flatten out. It's going to fall down. And we're only on this part of the pandemic scale. So again, like, this is something that should be concerning all of us. Anyway, we'll move on with the code. So this is something different. What we're doing here is we're plotting the number of hospital beds per thousand. And this is not a traditional graph like this. This is a bar diagram. And the way you make bar diagrams in Matplotlib is by plt.bar. Now I'm going to talk about what I'm doing here for some time. So you'll see that what's happening in the data set is that, okay, what's happening in the data set is that the number of hospital beds per day remained constant for more or less remained constant, right? Now if I ask Matplotlib to plot the number of beds, it's gonna get confused because it's gonna think that every day these people had a certain number of hospital beds, and that is true that every day we had a certain average per thousand, but we don't want that. We just want to have like some comparative analysis of how different countries are comparing against each other. So what we're going to do here is so ISO code is just the code of the country. So suppose India has IND and China has CHN. Now what I'm asking here Matplotlib to do is to drop the duplicates. What that means is that for each country, so I only want one value per country. So if there are multiple ISO codes of the same value, so if there are multiple rows with India, 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 I'm going to ask it to only keep the last one, which I think is a fair example, because some countries weren't just prepared initially, but then they did better as they figured out that, okay, they need more hospital beds. So what it's going to do is it's going to take China and it's going to take the number of death, it's going to take the total number of hospital beds per thousand on the last day of the reported data. It's going to take India and it's going to take the total number of hospital beds per thousand on the last day, because all these have a certain number, all these dates have a certain number of average hospital beds. It's going to drop all the duplicates and only keep the last one. And as I said, you need in place is equal to true to make any sort of changes in the data set. So this is what it's doing. I'm asking pandas to drop the duplicates. What duplicate? If there are duplicate ISO codes are just the country codes, and I'm asking it to only keep the last one. You can also keep first. You can also keep like if there is a certain index value that you want the middle one, you can do that too. Now, once I've dropped all the duplicates, I'm going to do this thing where I'm going to drop all the countries where I don't have data sets available. So if you look here,
Hello.
yeah.
Hello, sir. If they want any number in the middle, like 100, 200, should we type it as a string or integer?
It's supposed to be typed as an integer.
Oh, that was the thing. Okay, thanks a lot.
So if you see here in the data set, there are certain countries where you just don't have data available, right? So it's having 0 written and having nothing written are two different things for Python. So if there's 0, it still thinks that, okay, there is some data there and that the value of that data is 0. If there's nothing there, it's just not available there. So now what I'm doing is that there are certain countries where I do not know the average. And if I do not know that average, then there's no point of me keeping those values. So what I'm asking pandas to do now is from the data set, drop all these columns, drop all the rows where I do not know the average number of hospital beds. So drop NA looks at the subset hospital beds per thousand. And if there is any row where you do not have any data in that particular subset, it removes that value. So here we did two things. We dropped all the duplicates and we dropped all the rows where we did not know the hospital bed per thousand. Okay. Now, again, as we did last time, we're making one list of the countries. So from the data, I am asking it to read all the ISO codes, the country codes, and I'm storing it in a list called country. I am asking pandas to read from the data all the columns where there are where the hospital beds per thousand have been mentioned, and I'm storing them in a list called beds. And now I am asking Matplotlib to make a bar graph. What I'm doing here is okay, if I again there are a lot of countries, right? And if I just ask it to plot all these countries, then it will do that for me. Like this is what the graph will look like. These are all the countries and these are hospital beds per thousand. But you can't really see what's going on there. It's like too much information crammed in one graph. So what I'm asking it to do is, I'm asking it to, I'm asking Matplotlib to plot the values from 60 to 80. So these are only 20 values that I'm asking Matplotlib to plot. So if I look at the country list, I have a list of countries that is 165 countries long, and I'm asking it to plot the number of countries from the 60th rank all the way to the 80th index. And this is what it's doing. So now I have a smaller, I have the same size graph, but there are lesser number of countries there. This is, so as I said, that these are called ticks, and this is used to format these ticks. So X ticks applies to the ticks here, and rotation 90 just basically means that I'm asking it to rotate these values to 90 degree. I can also ask it to rotate these to 45 degrees, right? Since sometimes what you'll see is that you have longer strings which you can't fit in the graph, so it's usually helpful to rotate them so you can still have the complete names. You don't have to use short forms, and you can still see them. So yeah, so the reason why I chose India, why I chose this particular range, was because India was in this range. This is India, and you can see India has, you can see how it compares to the other countries. So these are the average number of hospital beds per thousand, and that's somewhere really low. And this is the number of hospital beds per thousand in Japan. This is the number of hospital beds in Hungary per thousand. This is the number of hospital beds per thousand in Kazakhstan, um, Iraq. So
What's the
India,
number for China?
yeah.
For China, what is the ratio?
We'll just,
There in this.
yeah, so China isn't plotted here because I'm only asking it to
Okay,
plot
okay.
this certain range. I can, so like there is a code to find out what is the index value of China, like where exactly in this list is China situated, and then I can ask it to do that, or I can simply go to COVID data and I can find China there, and I can look at the number of hospital beds in China, and that is that's where is the column for hospital beds? Yeah, this is the one. So for China, it's 4.34. For India, it's less than 2, I guess. Yeah, it's even less than 1. We have like 0.53 hospital beds per thousand people. So there's that. Yeah, I mean, like if you look at the data, it's slightly depressing and slightly scary to like expect what's going to happen, because like it ranks lower than a lot of the countries. Like, Iraq has better healthcare accessibility than India at this moment. But anyway, so this is some stuff that you can do with Matplotlib. This is plotting the total number of cases of India and China. This is plotting the total number of cases, total number of new reported cases per day in India and China. And this is hospital beds per country, per thousand. Another thing that I skipped here was that um, since pandemics have this exponential growth, one way to look at them is by using log graphs. Now, log graphs can be log graphs, or you can have one axis that is a normal axis and then one axis where there's a log axis. So to do log graphs, it's very easy in Matplotlib. What you do is you use semi-log, and you just type whichever axis is the log axis. So here we are using the y-axis as the log axis. If you want a log graph, then you just type log. And if you just want a normal graph, you just like ax1.plt. So again, we're making one figure, we're making two graphs in the same figure, and we're making two rows and one column. The first graph is dates and total number of cases, but the total number of cases are being plotted on a log axis. And I'm asking it to maximum put only 15 number of maximum only display 15 dates, date ticks. So again, this does not mean that it's only displaying 15 dates. It's displaying the entire range, but the ticks that it's displaying are only 15. So this is a semi-log graph where log axis is the y-axis. And as you can see that, so the thing with log is 10 raised to the power 0 is equal to 1, right? How do you get 0 in a log graph? You can't get 0 in a log graph. So it just keeps going to a smaller number. It doesn't actually reach 0 there. So now equal distances mean equal powers of 10. So this is 10 to the power 100. This is 10, this is 100, this is 1000, this is 10,000, this is 100,000. And as you can see that the graph here looks, so what I did here is it's the same data plotted on a log graph and on a normal graph. So this is a normal graph where it's where equal distances represent equal equal difference in value. So this is 10,000, 100,000, 200,000, 300,000. And as you can see that this is a exponential function here, but on a log graph, it looks different. So what this means is that once this log graph flattens, that means it's not, that means that there's going to be an, okay, so an exponential function on a log graph looks like a straight line. So a straight line going like this, okay, an exponential function on a log graph appears like a linear function on a, an exponential function on a normal graph appears like a linear function on a log graph. And the, okay, how did I forget this? What is that thing called? What does M represent in a linear line? Siddhartha, can you just remind me what does M stand for?
Slope.
Yes, slope. So so the slope of the straight line on a log graph gives you an idea about the exponential rise in the normal graph. Now, if this graph flattens out, that means we're doing good. Okay. And if this graph flattens out, what we'll see here is going to be an inflection. So if this flattens out, that means this will start dropping. So there's that. Now, like this, this goes into, like, to understand what's happening here, you need to understand some other terms like R naught, which is the reproductive factor, stuff like that. That will move on to next, because that basically, like, now this was all Matplotlib. Now I'm going to talk about epidemics in general, unless someone has a doubt until now. Is there anyone who wants to ask something?
Like, should we also discuss the significance of some of the things you chose to show us? For example, hospital beds per 1,000 people. You said, to be fair, you took the number of hospital beds on the last day mentioned in the data set.
Yeah.
So China has, okay, all right. Yeah. So, but I was just thinking maybe China went into so much preparation because there was an earlier onset of the disease. So, yeah, because I was thinking, wait, first of all, does that quantity make the parameter make sense? Because for a population like ours, it is probably not feasible to have that many hospital beds. So the ratio will seem smaller. But now,
yeah,
after that, China
the thing is that it's not the absolute numbers, right? In terms of absolute numbers of hospital beds, India would be far bigger than countries like Japan. Like, the sheer number of hospital beds available in India are far larger than whatever hospital beds are available in Japan. But it's about, so this one particular number represents the like availability. For example, if suddenly 1,000 people fall sick,
correct.
then for those 1,000 people, we'd be able to accommodate less than one.
Less than one, yeah.
So there's that. So like I want to move on to the 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 dynamics of an epidemic spread, but before that I just wanted to talk about something interesting that I find really fun, and that's 3D plotting. And I won't go into much depth about it, but I just want to like give you some idea that okay, 3D plots also exist and they look really good. um, so for 3D plotting you need this other library called um, MPL toolkits, which basically enables you to make 3D plots. And now I'm not going to go into all the details of the 3D plotting function, but so if you look at our other functions, for example, if we look at the kinematics function, it takes in one variable, that is time, and then returns a value of velocity. But there can be certain functions which take in more than one variables. So for example, if I take in two variables like x and y, and I return a third output, so I'm taking x and y and I'm doing some kind of math with x and y, and I'm returning a third output. So for that, you can't represent it on a two-dimensional graph, because if one axis is for um, one variable and the other axis is for the output, where do you accommodate the third variable? Then the third variable's value will have to be fixed. So in such cases, we use these things called 3D graphs, which, and this is not the only case you can do that. Like I do a lot of orbital design and I do a lot of orbital mechanics related stuff. And I love using 3D plots because I can actually visualize the change in inclination and things like that. So what I'm doing here is I'm making a list of two values, A and B, that go from -1 to 1. And I'm making a function that takes in these two values and returns a third integer. And now I don't work on lines anymore. Now I work on grids. So this basically creates a grid, and a grid is basically a tuple with two values. So so it basically creates like -1 1 -1 0 0 1 -1 0 for all these values. So A and B are enormous lists that go from -1 to 0.99 with the difference of 0.001. So it creates a mesh, and for every point in that mesh, it returns a third variable, and that third variable is the height from that mesh. Now what it's doing here is that depending on how far the third variable is, depending on how big the third variable is, it has this color map which defines how what color I want. So maybe I want that if a value is really close to the mesh, maybe I would want a color that is dark. Maybe if that value is away from the mesh, I would want a color that is light. So this creates a mesh, and I create a value called z, for the z-axis, that is the distance from the mesh, to these two values, and this creates a surface plot. So there are different types of 3D plots. There are surface plots. There's another thing called um, a wireframe. So this is a wireframe. You can plot surface plots. You can have different color maps for this, and so like this is I recently got this laptop, so I haven't installed the dependencies for Jupyter lab that I'm using. But if you're on Jupyter notebook, then you can also make these graphs interactive, so you can turn around these graphs, you can play with these graphs. If I've got some time at the end, maybe I'll show you how these graphs can be really useful, because you can turn them around. So these are 3D graphs, and these are also like they're not only useful, they're also really pretty, and I absolutely love 3D graphs. So now I'm going to talk about the dynamics of an epidemic spread, and that so the code for this dynamics of epidemic spread, this has certain dependencies, which, as I said, I recently got this laptop, so I haven't installed them. So I'm going to run it on Google Colab because then I don't have to install these dependencies. Um, And if you don't know Google Colab is basically just like Jupyter Notebook, but online. So instead of using your own computer, your own computing power, you're using Google servers to do that. And it's basically like Google Docs for Python code. Um, now, so the code, it's going to be a little alien because of this reason that this is optimized for making animations. This isn't optimized for making static plots. I use this code to make animations, so it looks slightly different syntax wise, but the math remains the same. And that is what I want to discuss now, the math of an epidemic spread. Unless anyone has a question, in which case I'll stop and answer those questions first.
What, I missed that. What did you say was optimized for animations and not static plots? The library.
The No, not the library. Like the library can do anything you want it to do. The code that I wrote. So like, so the code that I wrote does not make one. It doesn't have like a normal static list. It it appends the list every time the loop is run in order to make an animation for each frame. So what I wanted to say was that the code will look different because it's not the syntax that you would have come across in the previous Jupyter notebooks, because the previous Jupyter notebooks only made one single figure, and that's why they took all the values together and then they created one curve. The code that I wrote here, they took a small range, then it plotted a figure, saved that figure, then took a slightly longer range to created a curve. So it basically plots it frame by frame, and that's why it works slightly differently. Like the mechanics of the code works slightly differently, but the math remains the same. So um, and again, this isn't even the most optimized code for animations. The best way to make animations is to use while loops. I used for loops for some reason because I was just more comfortable with for loops. But okay, I'm going to talk about the math of the epidemic spread then. So the one of the most popular methods of um, so right now, like up till now, what we did was we used the previously existing data, right? We took the oh, why can't I? Yeah, in this Jupyter notebook we had an existing database. Oh, by the way, so I downloaded this file. If you want this to update every day, you don't have to like download the file. You can always just type out the URL. Whichever website is maintaining the database would upload that database every day. So every day, if you run the file, it will update the, it will take new database. So there's that. But what we were doing was looking at the past data to plot that data. This, what I'm going to do in this code is I'm going to have an hypothetical population of 100 or so people. I'm going to have like an hypothetical virus that's spreading amongst those people. So the idea is okay, I have this diagram that explains it better. So the idea is that you make these different compartments. Okay, so S stands for susceptible. Anyone who hasn't caught the virus is susceptible. E is exposed. So if I have been exposed to the virus, then I'm in this um, compartment now. I is infected. So when I actually start showing the symptoms, then I'm infected. And R is recovered. So once I'm recovered, I won't catch the virus again because my immunity has developed. And I make these different compartments, and that's why this method of um, understanding the dynamics of an epidemic spread, it's called the compartmental method. And what I'm and now I write differential equations. And some people, like, I don't know what's the age group of the people who are attending this session, but what these differential equations pretty much tell me is the rate at which people are going from one compartment to the other. Now, this is the rate at which new people are born in the population, and this is the rate at which people are dying in the population. This is the natural rate. Okay. So new people are born in the population. They're susceptible because they haven't caught the virus yet. A certain number of people from that population are going to die. A certain number of people are going to catch, uh, are going to get exposed to the infection. They're going to move to the exposed bucket. Then a certain number of people are going to die, and then certain number of people are going to start showing symptoms, and this keeps on happening. So what we basically define are the differential equations that tell us how the population is moving from one bucket to the other. So ds by dt is just change in the size of s with respect to a small change in t, and that is given by this one expression, which is the number of new people who are introduced in the population. Now these are certain parameters that are important to understand that. So as I said, that delta and mu were birth rate and death rate, like the natural birth rate and death rate. Without the without the virus too, a certain mu number of people would be dying every day. um, beta is the beta dictates the transfer of susceptible people to the exposed bracket. How many people are getting exposed to the virus, and beta is a value that will change if so initially people did not know about the virus and they were traveling in trains, they weren't following social distancing and stuff, and that time the value of beta was high. Now people are in their homes, now people are like washing their hands and stuff, they're getting less exposed, and that's why now the value of beta is low. So beta is just how many people are like how many people are getting exposed each day. Alpha is how many like how soon are the exposed people moving to the infected bracket. And alpha, you can think of alpha as the inverse of the incubation period. So if it takes one person 7 days to start showing the symptoms, if it takes 7 days for the virus to start showing the symptoms, like if one person is getting infected, is showing symptoms in 7 days, then in one day 1/7 of the people are gonna show the symptoms. I hope that I'm like making sense. So um, alpha is alpha is the inverse of the incubation period, and gamma is the inverse of the recovery period. So gamma is how quickly are people moving from the exposed bracket to how quickly are people moving from the infected bracket to the recovered bracket. So if it takes one person 10 days to recover from a virus, then every one day 1/10 of the people are recovering from the virus, right? So um, now this is uh, mu s. So we started with a certain number of people, that is susceptible population. From that, a certain number of people got exposed. Now this range of exposed people are now here in the exposed bracket. From exposed bracket, a certain number of people are going to die, and a certain number of people are going to start showing symptoms every day. So mu is the natural death rate. So a certain number of people are just going to die of natural causes, and alpha is the um, rate at which um, people are showing their symptoms. So from this exposed bracket, a certain number of people are going to get reduced and move on to the infected bracket. Now from the infected bracket, like if you see that this is the term here as well. So mu is so the mu e I've sent to a different compartment, that is dead people, because if you're dead then you can't start showing symptoms, and if you're dead then you can't recover either. So now from this certain size, a certain number of people are going to die, that is dictated by mu, and a certain number of people are going to get recovered, and that is gamma. And now again, mu I send to the death bracket, and gamma I send to the recovered bracket. From the recovered bracket, a certain number of people are just going to die, and but no one is going to get the infection again. So there's no beta term again. All right. So this is basically an SEIR model where you have these four compartments: susceptible, exposed, infected, and recovered. there are different types of models. For example, there is the SIS model, which is susceptible, infectious, susceptible. For example, if you get like common cold, you can catch common cold again. So there is no compartment for recovered people. So now you're looking at how susceptible people are getting infected and how they're becoming susceptible again. There is susceptible, infectious, recovered. For example, there are diseases with like very small incubation periods. So there are different models, and the one that we're using is the SEIR compartmental strategy. And what this is going to do is I have defined a certain population that is of 100 people. This is a hypothetical population of 100. I have defined these certain values as well for beta, gamma, and then I've defined how long I want to look at it, how long I want the entire animation to run. And these are just the functions that solve these differential equations here. So what I'm doing here is it's called numerical integration. I don't have an analytical answer to it. These aren't differential equations that can be solved on paper. So what it's doing is it's taking small units of time and solving it for every single unit of time. And that's something like that is very easy for a computer to do. Like simple calculations are easy for computers to do no matter how many times they're doing it. So now I have all these functions that are solving these equations for me, and I have these lists of T is the time array, S is the susceptible people, E are the exposed people, I are the infected people, R are the recovered people, and D are the dead people. And dead people are coming from all the brackets. A certain number of people are dying due to the virus that I've called omega, and a certain number of people are just dying for natural causes. So the D bucket here is getting filled by both the infected people and not infected people. Now I have defined a function that solves all these equations together and makes an array and updates and keeps updating these lists. And this is the
Hello,
plotting.
sir.
Yeah. Go ahead.
So what is that? So can you slide up a little bit? What is the zeros function? The zeros of steps plus one and float.
Yeah. Thank you for reminding me about that. So NumPy, NumPy has this function called zeros. Okay, what zeros does is, so here these are NumPy functions, but I've imported the entirety of NumPy. So I don't have to say np dot zeros. I've imported like NumPy, the entirety of NumPy. So I'm not calling a specific package from. So n zeros is a function of NumPy library, and it makes a list that is filled with zeros. How long is that list is defined by the first parameter. Now steps is okay. Yeah, I should have covered it. I'm so sorry. So t final is the number of days I want this function to run. So t final is 30 in our case, or 60. Yeah. So we were looking at it for 2 months. So t final is 2 months, and dt is um like how finely do I want to look at it. Do you remember we had like, so like we're looking at it every 0.1 days.
Yeah.
Okay, and steps is basically how many, like the number of times Python will have to perform these calculations, and that is the number of days divided by the precision that I want.
Okay.
All right. So steps is the number of times Python is doing these calculations. That is just how long I want this code to run, divided by how often I want this code to run. So what this is doing is it's creating a list that is steps plus one units, steps plus one long. So it can store this number of values. It can store this number of values, but as of now, it is filled with zeros.
Okay.
Float is just the type, it's just the data type of these values. So it can be an integer, it can be a float, it can be a string. I want it to be a float. Float is basically just, so what float means is, you can think of float as a decimal. number. So integers, like if the value is int here, it won't store the number 3.1. It will only keep the 3 part of it.
Okay.
So just like in the easiest way to explain this is just a decimal number. It's like slightly more complicated. If there's it's not complicated, there's just slightly more to what float data type is, but I'm sure like in one of the nakshatra sessions you'd be explained what float is. So yeah, so I've created all these lists which are which can store these many values, and they're filled with zeros for now. What I want is I want to step by step replace those zeros and um, replace those zeros with the value that I am calculating using these equations. So that's what I'm doing here. I've defined a function here that takes in all these lists and returns the other lists. And yeah, so they're solving the equations here. So ds, if you remember, ds is the function that defines how often is the rate at which the susceptible compartment is changing. De defines the rate at which the exposed compartment is changing. Like I've written a paper. So it's not a paper per se. It's I've written a document that explains this in much more detail, and it also has some sort of commentary from my end on like like on the entire pandemic in general, and that is written in a fashion that anyone who has any basic idea about mathematics should be able to understand it. It talks very little about the code, it talks more about the mathematics. So we'll share that paper with you, but this is basically a code that replaces. I'm doing that for every frame one by one. This graph is supposed to be empty, and I'm doing that for every frame, and then I'm using this func animation. Func animation is also another part of Matplotlib, which is helpful in making figures, animated figures. So func animation just animates these graphs. So I have like a lot of different frames, and I'm taking all these frames and I'm making a small GIF out of it. So this is what it looks like. So as you can see, okay, I'll open it in the
Karthik, you didn't include rate of infection spreading, right? In your differential equations. Like, did you have
so
that parameter?
yeah, so there's this parameter called the reproductive growth. Reproductive growth is the number of new cases today
Or old
divided
case.
by the number of new cases yesterday.
Got it. Yeah.
So reproductive, it's called R naught. It's R naught is basically what like R naught is the main parameter that defines all these things. And so R naught is the parameter that combines all these things together and turns it into one easy to understand number. You don't need R naught to solve these differential equations. You need these differential equations to come up with what the R naught is. And R naught is the number of new cases today divided by the number of new cases yesterday. Another way to think of R naught is how many people would one infected person infect tomorrow.
Okay.
So the way a pandemic works is if the value of R naught becomes less than 1, that means that the pandemic is slowly withering out, and the curve is on its the curve is falling now. If R naught is 1, that is considered the inflection period. So a pandemic is like the number of infected people keep growing until R naught becomes 1, and then as soon as R naught becomes less than 1, the number of infected people start decreasing. And what, like, again, if you want to like understand what are, how do you calculate R naught from these parameters, um, it's mentioned in the paper, but you don't need R naught to solve these equations, is the point that I'm trying to get across. R naught is a result of the outputs that come out of these equations.
Got it. So the rate of spreading depends on these functions,
Yeah, yeah.
basically.
Now, another reason R naught is helpful is okay, so there are certain constants here that are easy to define, like gamma that dictates um, how often are people moving from infected bracket to recovered bracket. That just basically means the inverse of how long people take to get recovered. Same is the case with alpha, that just is the inverse of how long do people take to start showing symptoms. But what do you do with beta? So beta isn't a constant that you know of. The way the way you do it in real life is you plot data, and then you look at the data, then you then you calculate the ratio of R naught, and from that R naught you calculate beta, because you so beta depends on a lot of things, but mainly how many people does one person meet, and what is the probability of that person catching infection from an infected person. So for example, the way you decrease beta is, for example,
So exposed to infected is, you're talking about 100% certainty that the person is definitely exposed to the virus, right?
yep,
But
yeah,
susceptible is he may or may not have been exposed to the virus,
yeah,
basically.
susceptible is the entire fraction that can get
That
infected.
can get
It
it.
doesn't
Yeah.
it doesn't mean that the entire population gets infected. It just
Mm.
means that they can get infected. So
Cool.
um, yeah, I was saying that beta depends mainly on these two things, that how many people does one person meet. If I meet like 20 people a day, and the probability of me catching infection depends on so many other parameters, like how often do I wash my hands, how physically do I meet them, do I hug them every time, do I shake hands with them, do I wash my hands after that, do people wash their hands after meeting me. So it depends on all these different parameters, and it's very easy, very difficult to pinpoint what's the value of this constant beta. So the way you do that in real life is you actually plot the data. You know how many people are infected, you know how many people are infected, so you plot that data, you calculate the ratio, which is the reproductive factor, and
Right.
then from that reproductive factor, you know the equation that decides that brings all these constants together, um, that brings gamma, beta, and alpha all together and converts it into the reproductive factor R naught. So that's another reason why R naught is so important, because R naught is easier to find than beta, and that's what you do.
Mm.
So yeah,
But
again,
I
like,
think I was referring to this other parameter where it's constant for a given virus. For example, if you have common cold or some form of influenza, it is known that an average person with common cold will at least infect, 3 people. It's something like that, right? So
yeah,
there is
that is also R naught. Like, it's the
that
same
is
parameter.
okay.
So
Okay.
so um, what
But in
we
that
talk
case,
about.
it should be constant for the virus. Oh, okay.
No,
So you're
it's
okay.
never constant. Like, whenever you talk about R naught, it's always the average R
It's
naught.
always
Because if you
dependent. Okay.
yeah, because if you think about it, even in a pandemic, like, this assumes that beta is constant throughout, but beta
Got
is not constant throughout. Like, when the number of exposed people and the number of infected people start rising, you start following precautionary measures, the government starts imposing lockdowns, you start wearing masks, and somewhere in the middle the value of beta changes, somewhere in the middle the value of R naught also changes.
changes.
So
Yes.
when we're talking about R naught, we're talking about the average R naught. So um, obviously it depends on the biological construction of the virus, but it is also a big function of the way humans are interacting in the society.
Also, did
So
you look up exactly how much of a role immunity plays? So, for example, if one has already been diagnosed and has also recovered, Are the chances of him getting COVID-19 again zero, or is there some negligible factor that we are
Yeah, so like there have been only a couple of handful cases of people reporting that they've caught COVID-19 again, and in almost all those cases, it just figured people just realized that they
they're not
never
fully
really fully
recovered?
recovered. Yeah,
Okay. Yeah.
they managed to subdue their symptoms, but they never fully recovered. They were discharged early. That's why like as we deal with the pandemic, we're figuring out, we're discovering things, we're figuring out how to deal with this more effectively. So yeah, it's a work in progress, but it doesn't mean like we should absolve ourselves of responsibility. So again, this is like the compartmental model. There's a lot more to it, which you might be able to understand when you go through my paper, which we share. But this was the bare bones of it. And Matplotlib, whatever Matplotlib you would have learned in this particular session, that should be enough to plot most of the things that you'd want to do. And yeah, that's it, I guess.
Cool. That was super information dense. So before we try to conclude, if Jawahar Babu is here, you can. Is he here? Okay, I think he just left. All right. So in that case, yeah, we'll close. So if there are any other questions, you can ask him now.
I'll stop sharing my screen now.
So Karthik, do you have any proper conceptual inferences from your mathematical analysis? Like something you can really say about either the situation in India or elsewhere?
Um, so one, like there are I talk about this in the document as well, which we would share. But the thing is that first of all, there has to be like one of the major flaws in any of these models is the reliability of the data in the first place. How many people are we testing, and how many people who get infections do we know are infected? Without those parameters, without like truly understanding who's infected and how many people are infected, we can't really do much with mathematics. The other thing is that as important as it is to reduce R naught, as important as it is to like mathematically, it makes the most sense to immediately impose the lockdown. But if you think about it, if you immediately impose a lockdown, people become paranoid, and then people start shopping, and people want to hoard stuff, and people crowd places and do all these kinds of things. And for that brief moment of time, R naught becomes much greater than it would have been in throughout the course of the pandemic. And that again is a slight complication. Like that is something that you have to factor in. Like how worse would it become if you immediately impose the lockdown? And lastly, um, an ineffective lockdown is worse than no lockdown. And that is a very controversial statement. But the thing with an ineffective lockdown is that if you think about it, so what happens in an ineffective lockdown is that people are still meeting each other and the virus is still spreading, right? And suppose you had a lockdown for 4 months, now you open it up again, but there are still infected people that you do not know of. Like you think that no one's infected anymore, but there are still infected people, because people were still walking around in the during the lockdown, and people did not report due to like social taboos and stuff. Now what happens is that a small fraction of your population is immune to it, but an enormous fraction of your population is still susceptible. And it's so obvious that the entire pandemic started from a single person. And if you've removed the lockdown and there's still a single person left, you risk facing an
The
entire
entire.
full scale pandemic all over again. And now you'll have to wait out for a longer, you'll have to wait out the entire duration again. So that's why some researchers suggested that okay, one way to do this is to have lockdowns in certain phases. So you let people know that okay, we're going to open things up again. You would be able to buy things, you won't have to hoard things, and we'll be able to make sure that you receive all the amenities and logistics that you require. And as important as the entire mathematics of it is, it's also like the on a policy level, it's also important to take care of all the other social factors. So The problem with an ineffective lockdown is that you won't fix the problem with a single lockdown. So you'll need multiple lockdowns, and that's going to be worse for your economy. So that, I mean, yeah, that's, these are some things that you just
One, I
really.
guess, like question that's been bugging me for a while now is that India, announced the lockdown fairly early in the onset of the pandemic within the country as compared to the other countries. So, for example, when other countries declared lockdown, they had probably reached a 10,000 or a 20,000 number, right? But India was, I think, in hundreds or maybe just around 1 or 2,000 when we had already gone into lockdown. And I think that made the economic effect a lot worse in the first 3-4 months, such that you cannot continue the lockdown. You have to forcibly you have to open things up again. But now is when we need the lockdown the most, right? Because now we are still in the ascending part of the graph. So don't you think the lockdown should have been postponed such that our peak coincided with it?
Yeah, so the thing, I'm not entirely sure. Like, again, I can't really comment on whether or not it was a good decision to, like, whether or not we should have imposed a lockdown later. But one thing which I am sure of is that when people knew that coronavirus is a thing,
Hmm.
um, there are certain steps that you can take which are not lockdown to prevent the virus spread, and that is like start testing early, start testing more people, just prepare yourself for the thing. And there are all these things that are not lockdowns, but those are also essential parts of um, controlling a pandemic spread. And these are things which like we we started stopping trains and flights way late. If we would have done that earlier, then we
Hmm.
probably wouldn't even need such an extended period of lockdown. And again, I'm not entirely sure whether or not India should have had a lockdown later or earlier. But one thing that was definitely a problem was that any lockdown should not be imposed in a matter of hours. So we knew that Corona is in India because we started preparing for it. But the lockdown announcement came like a few hours before the lockdown, and that created mass panic, and that just didn't give people enough time to psychologically and physically prepare themselves for the lockdown. And that was definitely one of the problems in my
Yeah,
opinion.
that's
But
from a social standpoint. But I think even from a logical standpoint, let's say proper lockdown, you just have 3 months of it, right? Anything beyond that takes a toll on the economy of the country. So where is or when is the best time to place those 3 months of lockdown? Would you distribute it? Would you put them in the beginning? Would you put them in the peak? I think that is an analysis that would be really be interesting.
no, that is a very obvious answer, because see, while pandemic spread exponentially, right? And every person can spread the virus to other people. So the best time to put a lockdown is as soon as you have the first reporting, and you're sure that this is the first reporting and no other people are
Yeah,
infected.
but 3 months later, when you release it and people start
Yeah, that's
going into the
definitely
public
a
and
problem.
spreading, and then it reaches the peak, and now you can't re-announce the lockdown.
Yep. I
So
mean,
I guess,
that's definitely a problem. And even when the lockdown was there, I don't know how effective was it. And
mm,
I mean, the graphs and all the data looks definitely really scary. But the so this isn't exactly like logic, or this isn't exactly mathematics or biomathematics, but this is still something that I'd like to end on, which is a slightly optimistic tone. Um, that see, the pandemic can't continue forever, and it can't even infect every single person in the population. And obviously we know that the mortality rate is very low. Like, a very small fraction of the people who catch coronavirus die because of coronavirus. So the thing is that since pandemic is going to end someday, with every day passing, we're definitively coming closer to the day when pandemic is going to end. And when that day is going to come, it's like no one can say for sure. But with every day passing, we're definitely coming closer to the day when the world is going to return to normal, and that's something which gives me hope, and I hope that that's something that gives you hope as well. So yeah.
Okay, thank you so much, Karthik. And for those who will watch the YouTube live either later or are watching right now, thanks for being there. And if you're watching this post-pandemic, I mean, we are just waiting to get to where you are. So hopefully that was informative. I think Karthik, you had like so much to say. It would be great for you to share the document with the rest of us.
Yeah.
We'll put it up on our GitHub as well, so you can access both the Jupyter notebooks and his document over there. Cool. So if there are no more doubts, we'll close.
And my thanks to everyone. And
Yes.
I thank everyone